Buenas tardes. Esta tarde el profesor Abur impartirá un seminario perteneciente a la Cátedra Andesa Red de la Universidad de Sevilla. Hoy es día 28 y mañana por la mañana impartirá otro nuevo. Este profesor es una eminencia en el campo de la energía eléctrica y pertenece al Departamento de Ingeniería Eléctrica y Computación de la Universidad de Northwest de Boston. Ha venido procedente de Roma y estará hoy y mañana aquí impartiendo.
It's good, thanks.
Ya sale por YouTube, o sea, que lo que se habla a partir de ahora.
No, let's switch off the micros. Ahora.
No. Now it's on.
Okay, so it's time to begin with the seminar by Professor Ali Abur. Let me briefly introduce Professor Ali Abur. He got the PhD in 1985 by the same year I got my degree. We were born the same month of the same year. We were married the same year. We had the same number of children. We published the first paper in the same year, in the same conference. Anyway, we have a lot of things in common. But anyway, so he has been a professor in Texas A&M University for, I don't know, over 20 years. Then he moved to Boston to Northeastern University, where he has been chairing the Department of Electrical and Computer Engineering. I don't know exactly the name. For until 2 years ago, until 2013. And he's an expert in many things, in power system and state estimation particularly, where he has been publishing, I don't know, hundreds of papers about state estimation, and a book that we co-author about the state estimation. He's a fellow of the IEEE and distinguished lecturer, and has been this year recently recognized with an award about the outstanding power educator. I don't know if it is the name. So this, so he's we are proud and very glad to have him here today. So he will talk about this new recent development in state estimation that we have not had time to talk about in state estimation because I was waiting for him, about PMU, the use of synchronized phasor in state estimation. So thank you very much, Ali, for being today with us.
Thanks. Thank you, Antonio. Is this okay if I stand here? Or yeah, okay. So thanks very much, Antonio. Also, I'd like to thank you personally and also the whole group for the invitation. It's always a great pleasure to be here. I've been coming back so many times, starting in '92. So it's been a long time. I've been in close contact with this group. So it's a great pleasure to be here, to be in Sevilla. So thanks again for the invitation. Also, I think I'm very privileged to talk to this group of very distinguished researchers. I know there's a very strong group here in power. So hopefully, you know, we can have a good exchange. What I'd like to talk about today is related to state estimation and specifically using phasor measurement units and what they bring and what they do not bring. What are the limitations, what are the advantages, and what are the new sort of things we can do with them, which we couldn't do with the SCADA conventional measurements. So before I move on, I just want to bring some greetings from Northeastern in case I'm sure most of you don't know it's where it is. It's in Boston, and of course there are a bunch of colleges in it, including you know, from business to College of Science and Social Sciences and so forth, but including of course computer science as well as engineering. So my department is under College of Engineering. And it's a good size university, 16,000 people, undergraduate students, 5,000 graduates. So hopefully if you come that way, we'll also have a chance to also have you visit the campus. So the outline of my talk today is this. So I'd like to talk a bit about synchronized phasor measurements. I'm sure most of you know, but just a brief introduction on the way, you know, we measure these and the way we consider the measurements coming to us, in which format. And then I'd like to talk about the phasor-only linear state estimator, which to rely only on phasor measurements. So we are assuming that there are enough phasor measurements in the system which will allow us to do state estimation. So there are a couple of formulations I'd like to talk about. These are alternative formulations. And then there's also the hybrid formulation, where we assume sort of the situation now where we don't have enough PMUs, but we have some. So how do you mix SCADA and PMUs in the same state estimation formulation? And then at the end, I'd like to talk a bit about how you can apply this Phasor measurement-based linear estimation to unbalanced three-phase state estimation problem in an easy way, sort of like a shortcut. So that's the outline. So to start, I'd like to highlight this book, which probably is well known by you now, the book by Fatke and Thorpe on synchronized Phasor measurements and their applications. The Phasor measurement as a concept probably existed for a long time, but physically putting it together and creating it as a device, as a prototype, was probably first done by Professors Fatke and Thorpe in late 80s. And then since then, you know, we've been seeing several manufacturers producing it, and you know, people are deploying them in power systems. So what is it? It's just a real-time Phasor measurement, and they use synchronization through GPS so that you can get, you know, phasors measured in a synchronized fashion at remote locations in a given system. And for us, the main advantage is that we can get you know, phase angle differences between two remote points in the system, which we didn't have earlier. Direct measurement of this didn't exist earlier. So here's the scheme. Again, you know, this is fairly well known. It's just a review. Essentially, here's the box, which is the Phasor measurement unit. The inputs to the box are voltages and currents, and the voltages and currents are coming from the primary. Of course, this is the primary signal. This is the power system, and they are collected by the instrument transformers, either a potential transformer or a current transformer. So in the secondaries of these instrument transformers, you feed them into the device, and the device essentially samples these signals, current or voltage signals, and stamps them, timestamps them using a clock which is connected to the GPS through an antenna. So essentially you're getting a very accurate clock to be able to timestamp these samples. So you essentially have a set of samples which are all timestamped, and these are sent to what is called the Phasor data concentrators. And of course, they may be configured different ways. This is just one configuration I'm showing. So it's as if, you know, it's receiving signals from different PMUs. It could be also receiving signals from another PDC, or it could be receiving signals from a substation of many PMUs and so forth. So this configuration may change. But essentially, you know, you get a lot of samples collected by different PMUs, and the job of the PDC is, you know, to time align them so that, you know, you pick up the, you know, timestamps which correspond to the same time instant, and you take those measurements and align them, and then you put them together in a fashion which is easily distributed or broadcast. And if you want to do it in a corporate setting, you may have a corporate PDC. You want to do it in a regional setting, you can do it like that. And of course, they can also be used for you know, engineering, planning, or other applications. So it could be in the background a scheme to keep them in a data storage facility, and then people may also use them for applications. So they may be used immediately, or they may be also stored and used for engineering studies or applications. And there's a very detailed report on it by IEEE Power System Relaying Committee. So I'm sure you can find a lot of details in that report if needed. So, so the bottom line is, you collect these samples, and from these samples you create corresponding phases, which will look something like this. And of course, you need a reference for these. So the reference turns out is the GPS, basically. So there is you don't pick one of these as your reference. You basically pick the GPS or the whatever that timestamp is on that signal as your reference. So there is really no reference for us. We do not pick a specific PMU as a reference PMU. So the other thing is, depending on the type of PMU, we may have we may be measuring voltages, we may be measuring currents, and of course these are all three-phase quantities. Like if you measure a voltage, you are actually measuring ABC phase voltages, and the same thing goes for the currents. And depending on the PMU, how many channels you have on the PMU, a PMU may measure one set of three-phase voltages plus several sets of currents. Like in this case, in this particular example, we are showing all these lines coming out of this substation being measured, these currents, and the voltage at the substation is being measured. So this PMU can measure sort of 1, 2, 3, 4, 5 times 3, 15 quantities altogether in individual phase currents and voltages. However, when it comes to reporting, the reporting will be done only for the positive sequence at this time. So in other words, once you get these individual three-phase voltages, for instance, then you convert them into the positive sequence value of those, and then you report just that instead of all three phases. Even though you have access to those, you can of course use them as well if you want. Okay, so those are the sort of a brief overview of what we mean when we talk about phasor measurements, what we mean by phasor voltage measurement, phasor current measurement. So these measurements come in, and in the old days when we did not have PMU measurements, we strictly relied on SCADA. SCADA stands, as you know, for Supervisory Control and Data Acquisition. And essentially that set includes power flows, power injections, of course, both field reactive and voltage magnitude and current magnitude measurements. So if you are using those measurements and you write out the equations for the measurements, they are nonlinear. If you consider X to be your state, which is basically the voltages at individual buses, and Z is denoting those measurements. So those measurements, individual measurements, will be a nonlinear function of the state. So it was quickly realized by Fatke and Thorpe and others, once phasor measurements became available, it was quickly realized that if you are explicitly using phasor measurements instead of SCADA, those measurements actually are going to be linear functions of the state. So therefore, this function h of x will be replaced by just a product of a matrix H, which is strictly a function of network parameters times the system state. So if you are using explicitly phasor measurements, then the model becomes linear, and this becomes the expression representing the measurement model. These are the measurements, which are the phasor measurements. Those are the voltages and the currents. Okay, this is a constant matrix. This is the state. And of course, we also allow for measurement errors because PMUs are not error-free. So that nu represents the errors, which are generally assumed to be sort of Gaussian or normally model. So far, there's really not a whole lot of new observation here. So these are well known. But turns out that the differences or the sort of changes to the formulation doesn't end there. So if you look more closely to at this equation and actually write it out, you know, since we typically use the weighted least squares estimation method to do the state estimation, you can formulate the estimation problem like this. So this is your linear measurement model. And then you say, okay, I'd like to make my estimate x, this x which you are trying to estimate, I'd like to make it such that when I try to estimate the measurements, which will be simply multiplying it by h, that estimated measurement, h times x hat, will be as close to the actual measurement as possible. And we sort of use a norm. In this case, we use norm 2. And if you use norm 2, which is here represented by square of these individual residuals, these differences, and then you weight them based on your assumed standard deviations or assumed variances of, or the inverse or the reciprocal of the variances of these individual measurements, then you try to minimize this, which will make this as close to z as possible in the sense, in the L2 norm sense. So that's the weighted least squares estimation. And in this case, since the model is linear, the estimate, this x hat, is directly available using this sort of product. And then here we are using this weight matrix R inverse, which corresponds to the covariance of these errors, which are sort of assumed to be normally distributed. And we make some guesses about this. So this is user defined. So we give some sort of assumed variance per measurement, and that's how we build R. So as a result, we get this direct solution or the expression for the estimated value of the state. So this is how we apply the weighted least squares as state estimation for this linear model. The thing is, knowing this allows us to go a bit further because we also know the structure of H. And if we dig into it, we discover that there are further simplifications possible in this formulation. So that's what I'd like to show next. So what we will do here is we will assume that for the sake of simplicity here, we are going to assume that we are measuring everything possible. So that means we are measuring all the bus voltages in the system. So these are complex values because we are talking about phasors. So these are the voltage phasors at each and every bus in the system. And we are also measuring currents along each of these branches in the system from one end. So if we write it out like that, the measurement vector looks like this, a bunch of voltage phasors and a bunch of current phasors. And then we can write it in terms of the state, which is nothing but the voltage phasors at each and every bus, which is essentially the same as this, but not the measured value, but the actual value. So that will be the state and plus the measurements errors. So if you write it out now as a function, you notice that this is the same as that, except these are measurements, these are the actual values. So we put the identity matrix here. And then for these, you can write it out like this, where this product is the product of the branch admittance matrix, which is sort of a diagonal matrix. And on the diagonal, you have the admittances of each of these branches that you are measuring the currents through. And A is the branch to bus incidence matrix. So the product will relate the currents, measured currents along these branches, to the voltages at each bus. Now, at this point, I have this note here saying that the shunt branches are neglected. And the shunt branches, what I mean by shunt branches are in the model for the lines. When I talk about branches, they can be lines or transformers or anything like that connecting two buses. If it's a line and it has this pi model with the shunt branches, we are ignoring them. If it's a transformer, the same thing. We are ignoring the shunt branches. So when you write the current expression, it's a simplified version of that without the shunts. So at this point, we are neglecting them, but we will introduce them later. So when you neglect them, then you can write this expression in a sort of simplified fashion. So before I do that, let me say that we would like to work with actual real numbers rather than complex numbers. So we take this measurement vector z, and we express the measured values in the rectangular coordinates. For the voltages, you have real imaginary parts, currents, the same. And I go back and I write this branch admittance matrix also in complex form like this. This little g and little b are both matrices, diagonal matrices. And then, if you form this complex matrix and call it H sub f, and this is E plus JF here, which is the same as that, except this is the true state and the measurement errors. This becomes the complex equation for the measurements. Measurements will be given by this complex matrix times the rectangular coordinates expressed state vector plus the error. And then we can split them into real and imaginary parts, blow up the dimension, but make it real. So this is the same as before, except everything here is now real. So I split these into real imaginary parts on the left, on the right. So this becomes the equation for, this is the same equation as this equation, except everything is now in terms of real numbers. And then, therefore, this H is a real number matrix, and these are real numbers and so forth. So this is, so far, this is just a expression of the measurement equation. Now, at this point, if you go back and apply the weighted least squares logic to do the state estimation, we need to build the so-called gain matrix. So this is the matrix I'm talking about here. So in this formulation, to be able to obtain X, you need to form this product. And to form this product, you need to form G so that you can use it here. And you can see here that you need H and R and so forth to form G. And that's what I'm doing here. Now that I have H, and I know R, I can form G. So if you look at the form of G, which is basically, I'm doing something which is typically done. I'm saying that R is an identity matrix. This doesn't really bring any limitations. I'm just doing it for simplicity. You can always bring it in and add it in here. So forgetting about R, essentially G becomes H transpose H. And with this structure, if you form H transpose H, you find that it becomes strictly block diagonal, which is very interesting because we are not really doing any approximations other than ignoring the shunts. I'm ignoring the shunts of branches, but other than that, I'm not really doing any approximation like we do in fast decoupled load flow. I'm not, trying to assume resistances are small, reactances are large, and this and that. So I'm not doing any kind of approximation. So as a result, what we get is a block diagonal G. Not only that, the blocks are identical. So the corresponding blocks, these two blocks are identical, and it's constant, and it's independent of the submatrices are identical. Now, of course, you can go back and say, okay, but you neglected the shunts, so what about those? So we have to take into account that and correct it for that assumption, relax it. So the way we do it is we say, okay, let's go back to the original equation. This is our original equation. And in this original equation, what I did is I split this H into two components. The H that I'm using, which ignores shunts, and then this additional H, which is very, very sparse, which is added on, which adds the shunts. So we are ignoring this initially. And so if you take this H times X and factor it out and use the rest of it as if it's an error, so that H due to the shunts times X plus nu, I call U here. So you can say, okay, this is my new measurement model, and this is my H, which is an approximate H, which is ignoring the shunts. And that's my error. Unfortunately, that error is no longer Gaussian, right? It's a biased U. Why? Because if you look at the expected value, it's just this times expected value of X. So, so what you can do is we can say, okay, the expected value of X as calculated based on our approximate H is this. So we can take this and correct it by taking this Z and correcting it by moving this. Since I know that this times the expected value of X is the expected value of U, I can correct it for this U, or the bias, by subtracting that expected value from Z here. So that becomes our corrected X. And if you look at it, it's actually the actual X hat, which we already calculated, minus this product. But it turns out that this product is very, very easy to compute because this is extremely sparse. And of course, we know how to do this kind of computation very fast because G is sparse, we have the factors and so forth. So this correction is very fast. Normally, you would have to do it iteratively because, of course, this is not correct, right? This is an approximation. So you have to do it iteratively until it converges. But in practice, because shunts are so small, we notice that one correction is typically more than enough as far as the tolerance goes. So, so that's basically something we tested, implemented, and tested. I'd like to show you some numerical results here. So these are for different test systems of different sizes, going from hundreds to thousands of buses, and therefore different number of Phasor measurements. We looked at error-free case as well as single and 5 bad data cases. Okay, so these are basically showing that the decoupled weighted least squares, which is what I tried to explain, and the conventional weighted least squares, they give the same mean squared error, which means accuracy-wise, we are not really losing anything. For all these cases, you can see they are matching. But then if you run it many times and look at the CPUs, you also notice that you gain also some, as expected, about half the time. So especially for a large data set, like in this case, a large system, the computation time drops roughly to half. So so that's not a huge advantage. It doesn't move the computation time by an order of magnitude, but it certainly reduces it. And then it may also motivate additional shortcuts or parallel processing applications, so forth. So there is that sort of potential if you consider these PMUs in this fashion. So the alternative to weighted least squares is the so-called L1 or LAV, or the least absolute value estimator. So this is, if you look at the problem formulation, it's almost identical to weighted least squares. The only difference you can see is the fact that we are not using the squares of the residuals. Instead, we are using the absolute value. So if you use the absolute value, the main difference is which you gain by using this formulation is robustness. That is, if you actually formulate the problem like this and solve it for x hat, it tends to automatically get rid of or reject bad data in the system. So when you get the solution, even when you have measurement errors, those measurement errors will have almost no impact on the estimate. And therefore, you get this unbiased estimate or much less biased estimate when you have gross errors in your measurement set. Well, you know, it has been known for years, almost like 30, 40 years since people looked into this and implemented it, but it has never gained traction. The reason was because it has a significant deficiency, and that is that this method had been vulnerable to the so-called leverage measurements. So what are those leverage measurements? I'll try to explain next, but you know, this deficiency sort of defeated the purpose of using LAV, because even if you had this sort of implicit robustness, anytime you run into these special kinds of measurements, leverage measurements, you lost that robustness. And not only that, this was already computationally more demanding, especially in case of SCADA measurements, when you were using SCADA measurements. So it just defeated the purpose, and there was no reason for you to go and implement this, which was a much more difficult, more complicated algorithm. It took longer to converge, and it had almost the same type of deficiency as the weighted least squares. That is, even if you had one leverage measurement which was bad, it would you know, bias the estimate. So because of that, it wasn't it didn't catch on. Now, before we look into it now with the Phasor measurements, let me just say a few things about the leverage points. What do we mean by leverage points? Okay, okay, so before I say anything about this, those of you who may know what critical measurements are, you know, the critical measurements are the measurements which are needed for observability. In other words, if you lose a critical measurement, you lose observability. And then, of course, you don't want to have critical measurements, because if you have bad data on a critical measurement, since it's needed to do state estimation or to make the system observable, that bad data cannot be detected. So all critical measurements are vulnerabilities for the system and so forth. So critical measurements, we know, are bad, and we can easily identify them. We know that they shouldn't be in the measurement set, so forth. Now, leverage measurements are sort of like the stealth critical measurements. They behave like critical measurements, but they are not critical measurements. So when you go through the tests to identify critical measurements, they are not going to pop up. They are not, you are not going to be identifying them, because they are not really critical. And in fact, when you remove them, the system will still remain observable. So they are not critical measurements, but when you do the state estimation, they behave like critical measurements, meaning if they carry bad data, they will bias your estimate, but they are not going to allow you to detect it by the statistical techniques. And how do they show up? How many are they? Where do they show up in the power system? Well, it turns out in an old paper from '94, Lamin Milli and his co-workers, they have identified the conditions, how they show up, and some of them are listed here. For instance, if you have flow measurements on lines whose impedances are very different from the rest of the lines, those flow measurements will appear as leverage measurements. And then, of course, if you are using very large weight, equality constraints, like if you have zero injections, you can always put very large weights to those measurements so that they are enforced. So if you do things like that, you create leverage measurements, and the way they are measured, they are created. I mean, visually, if you look at the Jacobian H, or the weighted Jacobian R inverse H, you will notice that the row corresponding to this leverage measurement will stick out in terms of the magnitudes of these quantities, and they will be quite different in terms of their magnitudes. They will be disproportionate to the remaining rows. And if you, for instance, if you consider an injection measurement, typically in the case of an injection measurement, you have a large value in one of these entries, and the others will be much smaller. And you know, it's not an easy task to bring them all down to a reasonable level. And in the case of flow measurements, you have a way of doing it by scaling, but for the injections, definitely you cannot do it. And also, in general, for the nonlinear solution, from one iteration to the next, these things may change. And handling these and getting rid of leverage measurements is a problem. Now, if you consider PMU measurements, phasor measurements, instead of SCADA, things suddenly change. The reason is because H only involves voltages and currents. Voltages do not present a problem because they have only one entry per row. And currents also do not present a problem because they only have two, or depending on the way you present it, 4 entries, but those entries are all at the same order of magnitude. And you can always multiply both sides of the equation by the same scalar and scale them down or up and bring them to the level of the others. So scaling is a trivial way to get rid of the leverage current measurements. And once you do that, you can guarantee that there will be no leverage measurements in your set. So this is an advantage over using the SCADA measurements when it comes to applying L1 to state estimation. And furthermore, if you have zero injections, if you want to use them, it's very easy because L1 uses linear programming, and equality constraints are almost implicitly taken care of in linear programming. So those things you can easily do without changing the weights. So there's no need to play with the weights, and that's not going to cause any leverage. So this is an advantage, and we can certainly take into account this advantage and now relook or revisit L1 to see what happens now that we have these advantages if we do it using the phasor measurements. So if you generally, so this is like a summary of what I said. So we have certain advantages after so many years, after 30 years. First of all, we have a much more efficient LP code. Some of them are even free. You can just download them and use them. And they can work with very large scale systems in a very, very computationally efficient manner. Second, as I said, simple scaling can be used to simply get rid of all the leverage points, assuming you are only using phasor measurements. And then, of course, we know that without leverage measurements, we don't have any worries. L1 estimator hopefully will automatically reject bad data, and then this bad data processing being built in will give us an advantage, and we can use it that way. So, so to compare the two, in the case of WLS, we need to go through a post estimation bad data processing. This is an iterative or cyclic procedure. You can only do it one bad data at a time or one incorrect measurement at a time. And depending on the number of bad data, this may take a long time. And it's fairly computationally heavy process because of the requirement that you need to build the covariance matrix of the residuals. Now, in the case of L1, the problem is solved only once. Now that the problem is linear, there is no external iterations like we did have in the SCADA. So that's one advantage. The second one is there are no leverage points, so we are sort of guaranteed to have bad data automatically rejected. And then, of course, the choice of the initial basis impacts the solution time. And if you are using it in sort of a real-time or in sort of in online fashion, then you can also take into account this. Always start with the previous solution. That will also add to the computational efficiency. So here's an example just to illustrate how easy to get rid of the leverage points are. In this case, we have intentionally created a leverage point for this current measurement here along line 1 to 2. And then we introduced bad data on that leverage point, leverage measurement, and we didn't do, intentionally, we didn't do scaling, and then we introduced scaling to show the impact. So these are the results. So this is the true solution. And when we introduce bad data and the leverage measurement without any scaling, you notice that these solutions are incorrect. You know, instead of this true solution, we get that. Instead of this, we get that, and so forth. Even though the rest of the solutions are correct. So the impact is very local. And then you do scaling, and then you get these correct solutions. So it's just a small illustration of how this works. And going with the much larger utility system, about 3,600 buses. And here we are using LAV versus WLS to compare the times, CPU times. And you notice that when there's no bad data, WLS is much faster because L1 goes through this LP solution. So it's much more computationally demanding than this. So it's at least 1.5 times faster. But then when you start introducing bad data, the post-processing takes much longer depending on the number of bad data. And you can see that it will increase almost linearly with the number of bad data because it's a cyclic process. We didn't test any of the other techniques like reweighted least squares and so forth. One reason is those techniques are more meaningful in the case of SCADA or in the case of nonlinear problem, because the nonlinear problem solution is iterative itself. So during those iterations, you can reweight everything. But in this case, the problem is linear. So you can actually get the solution in one shot if you are using WLS. And then if you are using weighted reweighting, then you turn the weighted least squares problem into an iterative problem, which defeats the purpose of using this linear formulation. So you can certainly use it instead of this post-processing bad data detection, but it will be the same because it will be another iterative process doing these reweights. It might possibly take shorter time than these, but of course, then you are not guaranteed to find bad data because reweighting is not foolproof. So given that, it looks like, I mean, these remarks are based on all these observations. It looks like when there is no bad data, WLS is fine and it's faster than LAV. When there is bad data, I think LAV performs comparable or depending on the number of bad data, sometimes better than WLS. And of course, the advantages become more pronounced by as you increase the number of bad data. And then, of course, all this assumes that you are doing this post-state estimation bad data processing for WLS. Alternative is reweighted WLS, which is possibly faster than this, but less reliable in terms of identifying and throwing out all bad data. Okay, so there are two summary slides just to wrap up what I tried to say so far. This one is over the past 30, 40 years, this is what we have been doing. And in this sort of implementation, where the measurements are, flows, injections, voltages, and so forth, this set weighted least squares is definitely a sort of a preferred alternative because it's well developed, it's widely known. We know it's non-robust, but we can do normalized residual tests, and also we can also apply reweighting. Any of these things will work to identify, detect, and remove bad data. LAV was not competitive because it was computationally slow compared to this. But more importantly, it had this deficiency because of the leverage measurement. So it just defeats the purpose to use this because it's as non-robust as this when it comes to leverage points. In the case of phasor measurements, where you have only phasors, then we notice that we can use scaling to get rid of leverage points, but because of the linearity and because of this computationally efficient linear programming packages, LAV certainly becomes advantageous and sometimes even more than competitive compared to WLS. So that's sort of the summary of all this. Okay, now coming back to today, because today, as you know, we don't have systems where PMUs are so widely deployed that you can do state estimation just based on phasor measurements. There are very few systems maybe you can do it, but it's not widespread. So we are faced with this challenge of using mixed or hybrid measurements. You have to use SCADA measurements along with phasor measurements. So what we mean by that is, the SCADA measurements, those power flows and injections and so forth, they come in at a certain time, and typically nowadays we receive them every few seconds, 3 to 5 seconds. And the state estimator itself actually runs at a much slower pace than that, maybe every 30 seconds or a minute, or sometimes even longer. Given the fact that PMU measurements are available 30 to 50 times a second, you can imagine, between the two scans of SCADA, like every 2-3 seconds, you will receive almost 100 or more PMU measurements because of their pace. So we are looking at a situation like this. You receive SCADA, and then for a while you don't receive any SCADA, you receive PMUs, and then of course you receive SCADA again, and so forth. So the problem, of course, is during this PMU refresh cycles, because of the small number of PMUs, you don't have full observability of the system. So these PMUs cannot really provide you full observability, but at the same time, you don't want to pass on the opportunity to do something with them because they are available. So how can we get these into the equation? How can we take advantage of them so that we have better visibility than just having SCADA measurements? So that problem is motivated by stuff like this. This is a recording I picked it up from Schweitzer Engineering website or brochure, where they show separation of phase angles in a given system. This actual recording. And you notice that this is 11 o'clock, 11:09, 11:24, 38:52. And you can see it takes almost close to an hour before this thing splits. And you're watching this split if you have a way of tracking these in real time. So So even if it's faster, let's assume that it happens within a few minutes or 3 minutes or 5 minutes. If you have a regular state estimator which runs every 2-3 minutes, you may run into a case where you may miss this because it's too slow. Even though this is not very, this is fairly slow, state estimator may not be sufficient. The scan rate of the state estimator may not be sufficient for this. So here's an example. For instance, if there's a voltage collapse which goes down like this, and these are the SCADA measurements, and in between you have Phasor PMU measurements. So it is quite possible that by the next SCADA scan, things have been too late to do anything. So, but instead, if we can somehow manage to track this by these Phasor measurements, then we might be able to, correct the situation. So, so we suggested to do this. So you just run your classical weighted least squares estimator when you have the SCADA measurements. And then we said, okay, let's switch to L1 or LAV estimator for the PMUs for two reasons. One, the PMU measurements are now linear measurements. I mean, the formulation is linear. Second, we would like to eliminate, so in sort of an automatic fashion, those measurements which will have a bad impact or which will appear as bad data to these, which is a small set. It doesn't cover the entire system. It's not enough to do the full observability of the system. So here's the flow chart. So essentially, you have both PMU and SCADA coming in at a given time. You use the classical weighted least squares. You do the estimation, and then you receive the next PMU. So at this point, there are no SCADA measurements. You just receive a small set of PMU measurements. You use an LAV estimator to use these, plus to use sort of the leftover SCADA from the previous instance to do an update. And we check if there is new SCADA here. If there is none, you go back, and now using this updated state, you update the SCADA measurements. You can actually calculate SCADA measurements. So those that you received in the previous scan will get updated. Not all of them, but some of them will get updated. And with these updated SCADA and the new set of PMU measurements, you do another update. You continue these updates in this period between the two SCADA scans. And then until that time, when the new SCADA arrives, you go back and you, of course, sort of start from scratch, and then you build your weighted least squares estimator again with the SCADA. So this idea of updating the SCADA measurements with the small incremental update based on the intermediate solution was suggested in the last IREP by Van Katsum and his colleagues. And however, they used weighted least squares for both. And when you do that, you open it up for errors because weighted least squares doesn't have any filter unless you explicitly process bad data. And it may not be easy because of the fast pace of things at the PMU scan rate. So, so we tried both actually, and we sort of created a collapse scenario like this. Here in this system, the voltage collapses here, and we don't have any PMU at this bus where the voltage collapses, but we have PMUs at buses nearby. And with that, if you compute the errors, mean squared errors, or the deviations with respect to the true state, LAV performs slightly better than just using WLS. And also, if you look at the actual trajectory of this voltage drop, this is the true trajectory. using LAV, which is shown in red, you do slightly better than if you used weighted least squares. And here, the reason is there is really no bad data here. The reason why we get better results with this is because since you are not covering the entire system, since the system is not PMU observable, inherently there are errors the previously scanned SCADA measurements. By updating them, you correct them a little bit, but still most of them remain bad, remain incorrect. So LAV has a better way to identify and eliminate those bad data than WLS, which sort of averages them. So that's the main reason. I mean, intuitive explanation may be this. But also you notice that it takes slightly longer than that to do this. So average runtime is longer for this than that. Okay, so here are some more results. I'll just skip them quickly. This is a much more realistic scenario maybe, because what we are doing is we are looking at a 10-second interval of a scenario where you receive SCADA measurements every second. So you get 10 SCADA measurements, and then you receive in between these, you receive 30 PMU measurements per second. So 30 times 10 gives you 300 PMU. So you have 300 PMU measurements, yet 10 SCADA measurements, and every second you have an update because you collectively use WLS to collectively process the SCADA and PMU measurements simultaneously. So if you do this and then run it both using WLS and LAV, you get these results. These are the mean squared error results, and we did this with several different number of PMUs. I don't know if it shows here. Yeah, it doesn't show. I'm sorry. This was this didn't show up in the PDF, obviously. I had several slides here showing how the errors change as you keep increasing the PMU. So we tested it with 14 PMUs, which is about 1 every 10 buses in a 140 bus system, and then with 30 buses, 60 buses, 90 PMUs. So as you keep increasing the number of PMUs, the performance gets better. And in all cases, LAV performed. These green ones are the LAVs, and these are the buses here, basically 140 and plus another 140, because we are looking at voltages and phase angles as variables here. You can see that the errors associated with each one remain very low for the LAV, and for the WLS, you see these spikes. And then you can also try it with bad data, which we did intentionally, zeroed some of the SCADA measurements. And then in that case, the picture didn't change much. Again, LAV remained fairly robust, and WLS, as expected, sort of gave us biased solutions. Okay, so let me quickly go over this last topic, which is the three-phase operation. Now, before we say anything about this, I'd like to bring up, I'm sure most of you know, fault analysis. You know, in the fault analysis, we use linear equations. So we use V equals ZI. Z is the bus impedance matrix, I is the injected currents and voltages, V is the bus voltages. So we use this linear equation, and then we manipulate it, and we come up with this sequence-based solution or sequence domain solution for fault analysis. So if you have an unbalanced fault, you can solve the problem in the sequence domain and then bring back the solutions and then get the solution in phase domain and so forth. So the reason why we can do it in the fault analysis is because the equation is linear, and we can apply this linear transformation and go to the model domain or the sequence domain and come back and so forth. Now, unfortunately, in state estimation and power flow, we cannot do it because we have the nonlinear equations, so you cannot apply this transformation, model transformation, to power equations. Power cannot be, split into the model domain. So therefore, if you were using SCADA measurements, there was no way of splitting this into modes and working in the model domain and so forth. Now, when it comes, when it switches over to the phasor measurements, as we have seen, the measurement equations become linear, and our variables are voltages and currents. So we suddenly have the same picture as we see in the fault analysis, except now these are the measurements. So therefore, it is now possible to apply model transformation. And the reason why you may want to do this is because if you are developing prototype programs like we did for the linear phasor only estimators, you have a program running with all these bells and whistles. You have the observability, you have bad data, you have this and that. So you have this full package which can handle positive sequence, single phase phasor measurements. It would be great if you can use the same program to do three-phase state estimation without changing anything. So how can you do it? Well, you can do it if you go to the model domain, because then if you split or if you decompose the system, these measurement equations into model domain, then you'll essentially get three, or sometimes if you have a balanced, fully symmetrical system, two systems which are identical. All you need to do is change the input data, and then you get the output, the sequence estimate. And then you can put them back together, and then you get the three-phase estimation result. So that's basically what we are doing here. So just a long-winded summary of this slide. I just said it. So we decompose the phasor measurements into symmetrical components. We estimate individual symmetrical components separately, and then transform the estimates back to phase domain to obtain phase voltages and flows. Here is the mechanics of things. This is the linear equation. These model transformations from fault analysis, I'm sure. In this case, of course, these are three-phase, so you may want to put it in sort of a big diagonal matrix. So each one corresponds to one measured three-phase measurement. So then by applying this from the left to each and every item, you get this picture. TZ is multiplied from the left by each item here. And then if you define this V like that, then the equation becomes that in the model domain. So Zm is the model equivalent of Z. This H is the model equivalent of H, and Vm is the model equivalent of V, and so forth. So you get basically a zero sequence, and if you are looking at a symmetrical case, positive-negative sequence set. So these equations are identical to the positive sequence. Everything else is the same. The estimation equations are the same. Gain matrices are built the same way, and so forth. So it's essentially changing the input data to the program and getting the results from the output using the exact same program. So if you do that, you get this result. We applied it to 3600 bus big system. We sort of converted it into a three-phase system, which is fully transposed, balanced, symmetrical case, but it should also work if it's not. So you see that these are the computational times for different estimators, weighted least squares and LAV. You notice that, whether you're doing it for zero sequence, positive or negative sequence, you get pretty much the same performance since they are similar equations. And then, of course, with bad data, you do the same thing. We see exactly the same trend as we saw in the positive sequence. The nice thing is you can also do bad data analysis here. You can detect, identify, throw out bad data in the sequence domain, and then come back and identify the corresponding phase, and so forth. So all these things are possible since everything is linear. the last thing I'd like to mention is, probably I'm a bit over time, but the last thing I'd like to mention is this. Now, there's this sort of, I shouldn't say misconception, but there's this belief that if you are having PMU measurements, phasor measurements, and several PMUs in the system, you should pick one of the PMUs as your reference PMU because you need a reference. Turns out that this is a bad idea because we don't know how PMUs are. I mean, each and every PMU has a non-zero chance of that it might be wrong, and if your reference is wrong, all other measurements will be wrong, and so forth. So, so when you do state estimation, it's better if you have access to PMU measurements. It's better, not better, but it's probably a must not to use a reference. Okay, so a good old slack bus, good old reference bus goes away. We have a reference-free state estimation formulation. So if you write the state vector, it will contain all the bus voltages and all the phase angles. None of the angles will be excluded or assumed to be a reference angle. So now you use the phasor measurements, and of course, your reference implicitly will be the GPS because these are timestamp measurements. So if you, since you are using phasor measurements or phase angle measurements, those phase angle measurements will have the same reference, which is unknown to us and we don't want to know it. The nice thing is, if you are using them as measurements and go through the state estimation bad data logic, then the bad data logic not only can identify and throw out, you know, SCADA errors, but they can also throw out PMU measurement errors. So if you have a bad PMU, that will be thrown out by the bad data processing function, whether you're using weighted least squares or LAV, or it doesn't matter. So, so this is something very trivial, but I think it's important. So I just wanted to mention that. This is also another reason or another sort of justification to using state estimation. Because without a state estimator, if you are saying, okay, forget about state estimator, I'm having very accurate PMU measurements, I'm going to do this application measurement based. So I'm just going to get the measurements and then use them in application. It's good as long as, you know, PMU measurements are good, but if any of them are wrong, there is no way to filter them. And if you have to use a reference, and some applications require you to use a reference, for instance, if you are, you know, looking at the phase angle difference, like a phase angle separation to capture some oscillation or something like that to remote points, if one of these are PMUs is wrong, there's no way you can know. And if this bad data constantly keep coming, you may think that things are separating. In fact, one of them may be bad data. So to avoid these sort of things, the best thing is to stick a state estimator in between. It will filter out those things for you. So I believe this was my last slide. Yeah. So yeah. So basically, we went over these two alternative formulations of state estimation when you are using phasor measurements only to do state estimation. And we knew all along that the main advantage was, you know, the formulation becomes linear and you can do the things, but that linearity has also other implications. For instance, it allows us to do this very simple transformation for the three-phase. It allows us to, you know, decouple the gain matrix and the WLS formulation and so forth. So those things are nice shortcuts, additional advantages we noticed. And PMU certainly will remain. I mean, they are here to stay. They are not going anywhere. So why not use them? I mean, definitely there is some logic or there is some controversy about whether we should deploy them just for this sort of application. Maybe not, but if you are deploying them anyway, which is the case nowadays, I mean, a lot of people are deploying them, So why not make use of them since they bring some advantages like this? So that's the bottom line. And I'd like to thank you for listening, and I'll try to answer questions if you have any.
Okay, thank you, Ali. Thank you very much. So then we need a wide microphone for questions. Please. Any questions this time? Any questions?
I have some. Thank you. You know me, I'm Esther. I'd like to know about the current cost of PMUs. So, because I think these new devices are really interested in order to, for example, develop a state estimators in distribution system where unbalance are important. But I'd like to know about the cost, the current cost of PMUs.
Yeah, I mean, I don't want to put a value because I asked the same question to the manufacturers and different utilities, and they give different answers, you know, going from $1,000 to $10,000. But I think the reason why it's not a direct answer is because I think the box itself is not expensive. I think the infrastructure, like if there's any fiber connection or antennas or the communication set up in the substation. So whether the substation is ready for this sort of installation or not makes the cost different. So the same PMU may cost different to different utilities depending on how their substation is right now. So that's my understanding. But the actual cost changes.
Okay. Thank you.
More questions? Any questions here? Okay, I have some technical questions about. We will give time to those guys in Malaga from preparing their questions. In the decoupled model of the beginning, you ignore shunt elements and then add it at the end in a iterative way. But I wonder whether if you are considering large shunt elements like large reactances or large capacitor banks, where they are not negligible. So have you tested this kind of shunt elements?
No, because you see, Antonio, the measurements are voltages and currents. So since currents only are functions of the line model shunts, the actual shunt at the bus never comes into.
Oh, okay. So this comes to my second question: is you also ignore, or apparently I didn't see
injections?
Yeah,
yes.
current phase or injection.
Yes.
You didn't include in the.
No, we don't have injections. We just have currents. We just have
but
currents.
Yeah, but not branch current. You can external branches can assign as injection, right?
Right. We don't have that.
Well, but PMUs actually they have it, right? They have them.
They have them. What we can do is, or what we do is, we create an artificial bus and make it into a branch. And this is
artificial impedance or something. Or
yeah, because anytime you have a current, you also have the sending end voltage. Because we don't have separate, like we don't have just current measurement. Typically, when the current measurement comes, it also comes with the sending end voltage.
Even if it belongs to another area, maybe not. If you cut the region.
Yeah, it could be.
So I'm adding an impedance, another bunch.
Yeah, good question.
Decrease the
include injections. So.
Yeah, this is a limitation because this reduces the redundancy that you may have if you include those measurements.
Yes, and then you also have to then use the shunt in that case.
Yeah.
But
so,
I don't know. We haven't tried it with a big shunt, whether you need the...
I think,
we are not iterating.
No, yeah, I think the decoupling will be valuable. I mean, okay, no problem. But what I see a problem is in the scaling.
the scaling with branch currents maybe not applicable, maybe the same problem as regular power injection, because they have difficult to scale in current injections in the same way it is difficult to scale power injection, right?
Yes, it's the same problem.
Yeah,
it's the same problem.
The same problem.
Yeah.
So this handling leverage measurement for the LAV may be difficult in case of branch current. I mean, injection current. Yeah.
Strict injection.
Yeah.
Right.
Yeah. No, another issue regarding the solution times is very tricky, because when you use bad data detection with the larger normalized residual, you should be very careful, and this is very tricky to compute the diagonal of the covariance of the residual. So, and this is, whether you use conventional factorization or from scratch, or computed the many elements of the inverse, or which technique did you use?
Yeah, we used, actually now there is a sparse inverse package provided.
Really? In MATLAB?
MATLAB.
Oh, yeah,
Yes.
I'm interested in this.
Yes, I'll give you the reference.
So it's a good news.
It's huge. I mean, it's just incredibly fast.
Okay.
So we are using that sparse
Perfect.
inverse.
So good news. So yeah, sparse inverse for us also. Antonio, please. Okay. So I think it's all the questions I have. We can continue, but for the time being, those in Malaga, all colleagues in Malaga, have a question, but there is a delay of nearly a minute or 35, 40 seconds. So, Jose Antonio, Pepillo, if you can enter, I'll try to connect my telephone, my Skype with your microphone. So let's see. Let's see if they are able to connect in real time. Otherwise, I will read the question. I have a question.
Okay.
But if they are able to enter in, online, I will wait. I will wait for the delay. Let's see. I have a Skype here, but You have any question?
By the way, regarding the sparse inverse,
Hi, José Antonio. Hi, Antonio. ¿Dónde está el micrófono aquí? Sí, te oigo muy lejos, poca voz. Tengo aquí el micrófono. ¿Me escuchas ahora mejor, Antonio? ¿Dónde está el altavoz aquí? Aquí, ¿no? El altavoz del teléfono está aquí, ¿no? Ah, en modo altavoz. Un momento. ¿Eso cómo se pone? Es que este teléfono es nuevo, a ver. Un momento, Pepillo, que voy a poner en modo altavoz esto, sí. Pero esto es Skype, ¿no? Esto es en Skype. Un momento, voy a poner esto en modo altavoz. ¿Dónde se pone esto en modo altavoz? Aquí, ¿no? Aquí. Ahora, a ver.
Antonio, ¿me escuchas?
Sí, a ver. ¿Se escucha? ¿Por detrás? A ver, habla otra vez.
Hello, everybody. Can you listen to me?
Ahora sí, ahora creo que te oyen. Sí, es que he puesto el micrófono detrás. Pregunta.
Okay. Thank you, Antonio, for organizing this very interesting talk. Thank you to Professor Ali Abur for a very nice topic and very good talk. I would like to ask a question regarding this. It is a kind of a very generic question, but I think Professor Ali Abur could share his opinion on this. With recent advances in communication and sensing, as well as huge investment in advanced metering infrastructure, there is a vast amount of data which previously was not available to system operators. Actually, this such amount of data is expected to exhibit exponential growth. So under this context, how big data analysis techniques may influence next generation state estimator? Do you think that we can expect progress in this area in terms of introducing new techniques, let's say some revolutionary techniques to existing state estimators?
Okay, thank you, José Pepillo.
yeah, thanks. Yeah, I guess he can hear me because I have the mic.
So, the microphone?
No, I have the mic. So
Okay.
Okay, thanks for the question. So
now the problem is they will be listening to you in real time here, and then 30 seconds afterward from the YouTube, right? So I will disconnect, Pepillo. You have any other question?
Yes.
Okay. No, let.
Question which is in your Skype.
Okay, I have Sebastian also connected. Once we finish, I will try to connect with him. Thank you.
Okay, so the question, I don't know if everybody heard it, but the question is, there's so much data now being made available to the utilities that, whether we can use this new techniques, big data, data mining and so forth, whether this is useful for state estimation. I mean, to the best of my knowledge, we haven't seen a whole lot of applications other than techniques which target missing data. So whether, since this whole thing is streaming in, so much data is streaming in, and there's a chance that you may miss or that there may be lost data occasionally. Is there a way to, first of all, check whether there's missing data? Secondly, whether there's a way, without really using any models or anything, I mean, network models, whether just using these big data techniques, can we replace this missing data so that the application doesn't really know that there has been this event or missing data in the stream. So those applications, I'm seeing people working on it and coming up with some results, which probably are useful if you have some application which strongly relies on availability of this high-pace, high-frequency data coming in. But I haven't seen any application of big data to state estimation problem itself so far. But I know that as the person asking the question indicated, I know that this is a problem a lot of people are mentioning in publications and talks and panels. So I don't know.
Okay, I have another question in this case, from Sebastián de la Torre, who is also in Malaga, a different connection, I guess. And he prefers I read the question on behalf of him in order to solve this technical problem we have with the delay. So I will read the question on behalf of Sebastián. He said that, what are your considerations regarding safety concerns, especially cyber attacks? In a modern era with more and more internet access, hackers may try to exploit weaknesses in communications. Is this a concern for system operator? Should it be?
Yes. Yes, I think this is a concern. I mean, I'm not an expert on cybersecurity, but when you talk to people in the utilities and national labs and so forth, they are concerned about this. My view is, I'm not an expert on communication, so there are all sorts of techniques people use, this authentication and this and that, so that they making sure, or they are watching the traffic on the network and then detecting unusual traffic, and based on that making some judgments about whether the data has been impacted, so forth. So those things I have no clue. I'm hearing from others, but for us, I mean, just looking at this as a measurement anomaly detection problem, it looks to me like a bad data detection issue. So if you can make your measurement set, measurement design as robust, as reliable as possible, meaning, you get rid of all your critical measurements, you put a certain number of local redundancy and so forth. So you design your measurement system in such a way that you can handle bad data. You know that you can detect bad data. Then I think you have enough power to at least detect intentional changes in measurements. Somebody is intentionally changing certain measurements. So my take is, I view the cybersecurity problem as a bad data problem, bad data detection, identification problem. So.
Yes, last week we had here an engineer from Endesa giving a seminar about the control centers and all this infrastructure they have for control and monitoring and including state estimation. And I asked him the same question, whether they are concerned about cybersecurity, cyber attacks. And he told us that so in those cases, they are not so much, there's no possibility for some hacker to get into the data and to modify the data arbitrarily. But they are really concerned at the distribution system because they are increasingly more frequently using public system, the GPRS. They contracting to utilities all this internet service and this IP. So every low voltage substation, secondary substation may have an IP address or this kind of thing. So they are using internet. In this case, they are really concerned because this is a possibility.
Yeah.
Mm. Okay, I don't have more questions. Sebastian says, thank a lot for your answer via Skype. So any other question? You still have time to make any other questions? Okay, thank you very much, Ali.
Thank you.
They say 20 seconds of delay, they say from Malaga. What do I say? 20 seconds of delay. Okay, not so bad.
Yeah.
Okay.
Okay, great.
Okay. It was shorter than expected. I was expecting more
Really?
longer. No,
Oh,
yeah,
I
because
thought I was-
no, it's not like in the USA.